Welcome back. In this module, we will discuss the very important topic of reversibility and reversible Markov chains. Intuitively speaking, a Markov chain is said to be reversible if the statistical properties of a chain with time running in one direction is indistinguishable from the statistical properties of the Markov chain when time runs in reverse. All right. And we will see when that happens, okay, in a little bit. So, that is the topic of this discussion. Now, I just want to start with recalling for you a Markov property which says that P xn plus 1 given xn minus 1 dot 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 x naught is simply equal to P of xn plus 1 given xn. Okay, this is no matter what values these xn's take. All right, this is true for all n and for all values of the states xn minus 1, etc. Okay, this is the Markov property. This can be easily extended. Okay, to look at this, you can look at probability of x n plus k x n plus k minus 1 dot 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 x n plus 1 given x n minus 1 dot 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 x naught. This you can show for if x n is a DTMC. For any Markov chain, you can show that this is simply, you can just use conditional probabilities and the Markov property to say that xn plus this will be equal to minus 1 dot 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 xn plus 1 given xn, which means that you can basically just forget about all of that, right? Conditioning on all of that can be thrown out. This does not require any further assumptions, right? This is true for I am just using the Markov property, and you can write it out in terms of conditioning and use the Markov property repeatedly to get this. All right, this is just a simple exercise. You may want to do this fully yourself. Okay. Now, I want to think of this xn as the present state. Okay, and all of this guy will be, all of these guys will be the past. Okay, and all of this will then be the future. All right. So more generally, so let me denote. So, at time n, I want to denote by a n plus any event which is determined by things in the future. All right. By future, I mean xn plus 1, xn plus 2, etc. So, index n, xn is my present state. Okay, index n is present time, and a n plus refers to at time n anything that is determined by future states. Okay, to be a little more precise, a n plus is an event measurable under the sigma algebra generated by xn plus 1, xn plus 2, so on. Okay, and a n minus as some event determined by the past. Okay, so more precisely, it will be some event in the sigma algebra generated by xn minus 1, xn minus 2 dot 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 x naught. Okay, so if you write the Markov property, so if you write that equation in this a n plus a n minus sort of notation, what you can show is that using this Markov property, we can show that probability of a n plus given xn a n minus simply equal to probability of a n plus given xn. All right. Essentially, this a n minus business can be thrown out, the past can be thrown out, it only matters where you are presently, right. And if you multiply this multiply both sides by P a n minus given x n, and what will you get? You will get P a n plus comma a n minus given x n. All right, I am just multiplying the left hand side of the above by that term. All right, you will get P a n plus given x n times P a n minus given x n. Okay. So, this is in some sense the most intuitive way to understand, this is true for all n greater than or equal to 1. This is in some sense the most intuitive way to understand what a Markov chain really is. Okay. So, a n plus 1 is, so x n is your present state. Okay. You are in, x n is in some state, let us say I, it does not matter what state. A n plus is things in the future, a n minus is things in the past. All right. So, a n plus can be any event measurable under sigma of x n plus 1, x n plus 2, etc. A n minus is similarly measurable under all events, all random variables from the past. You have the conditional independence, right. This is saying that there is conditional independence of past and future given the present. Right. So, conditional independence of the past and the future given the present is a very good, this is what Markov property really means. So, we knew all this, right, we sort of knew all this, I am just writing it down in a particular notation. Now, why am I doing all this? You will see very soon. So, let us go ahead and divide this by P a n plus given x n. Then what do I get? I will get P a n minus given x n comma a n plus is equal to P a n minus given x n. Okay, assuming that this probabilities are non-negative, I am just dividing by P a n plus given x n. So, what does this mean? This is saying that given the present and the future, the probability of a n minus is simply the probability of a n minus given the present. The future is irrelevant. All right. So, in some sense, what this is saying is that if time were to run in reverse, in which case, so if time runs like this, okay, n plus 1 is future and n minus 1 is the past. But if time runs the opposite direction, then n plus 1 becomes the past and n minus 1 becomes the future at time n, right. If you are at time n, running this way, n minus 1, n plus 1, right. So, n plus 1 is future, but if time runs this way, n plus 1 is the past, then there is n present, n minus 1 is the future, right. So, if time runs in reverse, right, what we are saying is that the past does not matter, past here is a n plus, if you think about it, right. In reverse time, a n plus is the past, right. So, this is some kind of a Markovian property when time is run in reverse, right, for a Markov chain. So, this is basically saying that if you have a Markov chain running in forward direction, right, and you note down all its states and you record this as a tape and you run the tape in reverse, then the reverse also has a certain Markov property in the sense that in the reverse time, future conditioned on the present is independent of the past, okay, but the future is a n minus now, right, because time is running in reverse and the past is a n plus when time is running in reverse. Okay. So, this is very nice, all right. So, the reverse process, so when time runs in reverse, reverse process also satisfies the Markov property. That is what the above equation is saying, right. Now, so if the above equation also is above equation is saying that if you okay, so a process is running like this, okay, you see a bunch of states x13, x14, x15, x16, and it run time in reverse, you will see x16, x15, x14, x13. We are saying that even in reverse time, a certain Markov property holds as given in that equation star. All right. Now, if the reverse process is also has a Markov property, then we have to ask what its transition probabilities are, right. So, let us say we are given the transition probabilities of the forward running Markov chain, which is the original xn process. Now, we are so x13, x14, x15 runs according to some Pij transition probabilities. Now, I run it in reverse x16, x4, x15, x14, x13. Now, these transition probabilities, what are they, right. So, that is our next task. So, we know that it satisfies a Markov property, we want to find out its transition probabilities. So, I want to try, so transition what are the transition probabilities of the reverse process? Okay. We know that the reverse process satisfies Markov property, then we want to find out what its Pij's are, right. Okay, let us say the forward chain has Pij as the transition probability, the reverse chain has some other transition probability, right. We want to know what its transition probabilities are. So, I want to calculate this I. So, let us say I want that, right, because when you are running, let us say when your Markov chain is running like this, right. Let me just draw. So, this is let us say x0, x1, x2, xn minus 1, xn, xn plus 1, etc. So, this is forward time and that is reverse time. Okay. So, I want to look at the probability that xn minus 1 equals j given xn equals I. So, this is like a transition probability of the reverse process. Okay. This I can just use Bayes rule, basic conditional probability to write xn is equal to I given xn minus 1 equals j over p xn minus 1 equals j times probability that xn equals xn is equal to I. Oh, I beg your pardon. Sorry, I think I got this wrong. I got this wrong. I should write p xn minus 1 equals j over p xn equals I. All right, this is simply the definition of conditional probability. So, now, so this is what this, so this is the transition probability of going from I to j in reverse time, all right. And what is that? That is the transition probability of the forward chain, right. So, this is simply p j to I, p j I. Okay. So, I am going to assume that the forward chain is a Markov chain, a homogeneous Markov chain with transition probability p j I. Okay. So, this is just the probability of going from j to I. Now, the issue is that this term depends on n, correct, because the probability of being in state I at time n or state j at time n minus 1, these are generally dependent on n, correct. So, the entire quantity, so pji does not depend on n, but the entire this ends up depending on n. So, what are we saying? So, if a Markov chain is running in the forward direction, if I just reverse the tape and run it in the reverse direction, I do have a Markov property. Okay, the reverse chain is also a Markov chain. Okay, that is what this equation star says. All right, but if I try to calculate its transition probability, this transition probability of from I to j ends up being a function of n, right. So, what does that mean? So, the reverse Markov chain, It's a Markov chain of course, but it is an inhomogeneous Markov chain. Okay. So, what are we saying? Even when the forward chain is a homogeneous Markov chain, the reverse chain, while is a Markov chain alright, it is an inhomogeneous Markov chain in general, okay, which is a slightly unfortunate situation, right. There is a remedy to this. If you assume that the forward Markov chain is started in the stationary distribution. Okay. So, we are now assuming that the forward chain first of all has a stationary distribution pi, okay, and we are starting the Markov chain, the forward Markov chain in the stationary distribution at time 0. Okay. So, for the forward Markov chain we are starting at the stationary distribution, which means the forward Markov chain will always be at pi, right. Then what happens is that this term out here will not depend on it, because this term will simply become pi j over pi I. Okay. Then what so in this case what happens is that you have p, so I will say then, so all this is assuming that there is a stationary distribution for the forward Markov chain and I am starting at the stationary distribution, then I can write xn equals I is simply p j I pi j over pi I. Okay. Now, this is not a function of n, alright. So, this is the transition probability of the reverse Markov chain Pij star, okay, just to denote that it is not the original chain, it is the reverse chain, I am denoting it by a star, okay. Pij star is the probability of transition from I to j in the reverse chain, okay, that is equal to Pji, which is the forward transition probability from j to I times pi j over pi I, okay, where the stationary distribution is assumed to exist, okay. So, let me just write this down. So, this is important. Pij star is equal to Pji times pi j over pi. Okay. And this is true for all for any states ij. Okay. So, what have we said so far? So, the forward Markov chain is running. If you look at the reverse process, also has the Markov property, that is what the equation star above says. But however, the reverse Markov chain has the slightly unfortunate property that the reverse Markov chain can be inhomogeneous even when the forward Markov chain is homogeneous. Okay. However, if you assume that the forward Markov chain has a stationary distribution and that the forward Markov chain is started in the stationary distribution, then the reverse Markov chain is also homogeneous, alright, with the transition probabilities given by this equation. Okay. So, the forward transition probabilities are Pij, reverse transition probabilities are Pij star, which are Pji by pi I times pi j. Okay. Now, that is not what reversibility is, right. I have not told you what reversibility is. I only told you that the forward Markov chain and reverse Markov chain have two different transition probabilities and I have derived the transition probabilities. Now, what is reversibility? Reversibility is the property that the reverse Markov chain has the same statistical properties as the forward Markov chain. That is, for any two pairs of states I and j, if Pij star is equal to Pij, then such a Markov chain is said to be reversible. Okay. So, again reversibility is not that if you run a Markov chain in the so if you have a Markov chain running like this, reversibility is not the property that the reverse Markov chain is also Markov chain. It always is, alright, and the reverse Markov chain is also homogeneous if the forward Markov chain is in stationary distribution. The reversibility is a property that the reverse Markov chain is statistically identical to the forward Markov chain. Okay.